An integral, section 5.2. Definite integral of a function f of x on an interval, closed interval a to b, is the limit as n goes to infinity, I equal 1 to n, f of xi star times delta x. Delta x is the width of each subinterval. X of I star is any point on the ith subinterval. It could be the right endpoint, it could be the left endpoint, it could be the midpoint, it could be some other point. The finite sum without taking the limit is called a Riemann sum. That's named after Riemann, who is one of the developers of calculus. He wasn't the calculus has been attributed. The invention of calculus has been attributed to Newton and Leibniz, but there's it wasn't just any one person. It was developed over a period of time. And Riemann was one of the ones that came later after Newton and Leibniz, and to sort of develop it further. The limit, if the limit exists, then f is integrable on the interval a to b, closed interval a to b, and the definite integral is denoted with this notation here. You can read this as the integral as a goes from a to b of f of x dx. So it's so the Greek letter sigma is used to represent sum, and this symbol here, they wanted something that was more I guess a little smoother curve or something to sort of suggest a limit of a sum. So this is that symbol there. You can think of it as it's like a smoothed out sigma to indicate they're taking the limit of a sum. Dx, you can think of that as the limit of delta x. The dx is like the width of the interval, but the interval width, when you take the limit, the interval width goes to 0. So anyway, this is the notation, so in the previous video, we had a sum that was like this for computing the area under the curve. This is kind of a more general, slightly more general notation. It could be if you have a curve that goes, you might have a function that was, let's say, went above and below the x-axis. Let's say this is your function here, and let's say this is your point B, and yeah, maybe this is your point A. And if you want the integral on from over the interval from A to B, the integral is actually going to be sums and differences of areas. So you'll have this area here, and then you'll have a minus that area. So in this, so before we had we were just looking with at a graph that was of a function that was above the x-axis on that interval, and the integral is just in that case the integral would just be the area under the curve. But if you have something that goes a function that goes above and below the x-axis, it's going to be sums and differences of areas. So you would add the areas that are above the x-axis and subtract the area below the x-axis to get the integral. That would be equal to the integral. Okay, and then so it's a slightly more general form than what we were working with before, and it's also more general because the number you pick for to compute the height of the rectangle could be any point on the subinterval. So it's usually convenient. I like to usually use right endpoints, but when you take the limit, it doesn't matter. You could use left endpoints, right endpoints, or some other point in between. It may make a difference in how fast the integral converges, but eventually it converges regardless of which endpoints you use. So if we want to compute this integral here, well, it's the same process we did before. It's actually basically we can repeat the same pattern. This is it's just that the notation has changed now. We want the limit as n goes to infinity of if we use the definition, the summation of I equal 1 to n f of xi star times delta x, and that's by the definition. It's on the interval from 1 to 5, and so it's going to be the limit n goes to infinity summation I equal 1 to n of if we use right endpoints, it's going to be f of 1 plus I times 5 minus 1 over n times 5 minus 1 over n. And so delta x is the going to be 5 minus 1 over n, because we're on the interval from 1 to 5, and if we're dividing it into equal intervals, they don't necessarily have to be equal intervals, but usually it's convenient to take equal interval width, okay, so and we're using right endpoints here, so it's limit n goes to infinity summation I equal 1 to n of f of 1 plus 4I over n times 4 over n. Okay, so then we can put in the formula for f of x. That's 2 times x plus 1, so replace x by 1 plus 4I over n. So this will be the limit n goes to infinity summation I equal 1 to n of 2 times 1 plus 4I over n plus 1 times 4 over n. Okay, so then we can distribute the 2 and add the 1. 2 times 1 is 2, plus 1 is 3. So this will be the limit n goes to infinity summation I equal 1 to n of 3 plus 2 times 4 is 8, 8I over n times 4 over n. Okay, so then we can distribute, so that time we were distributing the 2. Now we can distribute the 4 over n, and so this will be the limit n goes to infinity of summation I equal 1 to n of 12 over n, 4 times 3 is 12 over n, plus 32I over n. And then we can split up the limit and split up the sum. This is the limit as n goes to infinity of summation I equal 1 to n, 12 over n, plus limit n goes to infinity summation I equal 1 to n, 32I over n. This is over n squared. We have n times n is n squared. 32I over n squared. Okay, so I'll get another piece of paper here. Okay, so we'll have the limit. So the okay, so there's no I in the first term, so we can take the 12 over n outside the summation sign. So this is going to be the limit n goes to infinity of 12 over n times the summation I equal 1 to n of 1 plus, and we could take the 32 out of n squared out of the summation sign. The limit n goes to infinity of 32 over n squared summation I equal 1 to n of I. And this first sum is just n. It's 1 plus 1 plus 1, etc. n times. That's just going to be n. So I have the limit n goes to infinity 12 over n times n plus the limit n goes to infinity 32 over n squared. And then here we can use the shortcut formula. That's going to be n times n plus 1 over 2. That's the shortcut formula for the summation of I equal 1 to n of I. So the n's will cancel. Here the n's will cancel, and the 32 into 2 into 32 goes 16 times. So this is going to be limit n goes to infinity of 12 plus the limit n goes to infinity. We'll have 16, and we can rewrite this as n over n times n plus 1 over n. So I'm putting splitting up the n squared into to two pieces, and n divided by n cancels. The limit of a constant is just that constant. So this limit as n goes to infinity of 12 is 12. And we can write this as 16. If we distribute the denominator here, this is 1 plus 1 over n. And now we can take the limit. The limit of 1 over n is, as n goes to infinity, is going to be 0. The rest of them are constants. So 12 plus 16 times 1 plus 0, and that's equal to 28. So that's the same result we had before. It's just I was trying to regard it now as applying a definition of an integral. So before we were just looking at as a limit of rectangles, but now we're actually sort of applying the formula for the definite integral. Okay, so there's a couple other ways. We did it by taking a limit of rectangles. This particular one, we could use basic geometry. If we divide the area under f of x into a triangle and a rectangle, the area of a rectangle is length times the width. So this would be 4 times 3. The area of a triangle is 1/2 the base times the height. 1/2 times 4 times 1/2 times 4 times 8. So this 4 times 3 is 12. That's the rectangle. 1/2 times 4 times 8 is 16. That's the triangle. You can basically you can, for the rectangle you can just count the number of little squares in it. Each square is 1 by 1. So I don't know if it's probably hard to see the little squares on the screen here, but there's little, if you count the number of little squares, there's 12 of them. And for a triangle, it's a little bit harder to do it that way. It's sort of the same idea, but you have a bunch of partial squares here that will make it harder to count. But if you completed the rectangle here and counted the extended this triangle here to make it into a full rectangle. And you can count the little squares there. There should be 32 of them, and then divide by 2 to get the shaded area. So anyway, the area under the triangle is 16. Area under the rectangle is 12. It's 12 plus 16 is 28. So you can use, for this particular function, because it's just a straight line, you could use the basic geometry for it. Okay. Okay. There are some functions where the limit does not exist in terms of cannot be expressed in terms of elementary functions. So there's this definite integral, going back to the definition here, okay, so this limit is not going to exist for all functions, and also there are functions where the limit does exist, but it's not expressible in terms of elementary functions. So there are some functions where we are going to have to be satisfied with just taking a lot of little rectangles to approximate the area. And you can use computers for that to do that. We're not limited to 4 rectangles. With a computer, you can do 1,000 rectangles or something like that to get a pretty precise estimate of the area. So there's some functions where we can do it exactly, but there's other functions where we have to be satisfied with approximating. But this particular certainly with the linear function, we can get an exact method by taking the limit, exact answer with the limit. Okay, so here's another example of we have the integral from 1 to 4 of 2x minus 3 dx, and this one goes above and below. So the integral is going to be we're going to do the part that's above the x-axis with a plus sign, and the part that's below with a minus sign. So we want to let's see. So this looks like it's about 2.5. The base here is 2.5 or 5 halves for the larger rectangle, and the height is 5. If you count them, it's 1, 2, 3, 4, 5. So 1/2 times base times height, 1/2 times 5 halves times 5, 25 fourths. The small rectangle, the base is 1/2 and the height is 1. So that's going to be 1/2 times the base times height. 1/2 times 1/2 times 1 is 1/4. So that means that the integral is going to be the large rectangle minus the small rectangle. 25 fourths minus 1/4, 24 fourths, which is 6. So the integral doesn't always correspond to area exactly, but in its most general form, it corresponds to sums and differences of areas. Okay. So here's another example where we're using geometric methods. The integral of from -2 to 2 of 1 plus square root of 4 minus x squared. You may recognize this from pre-calculus. This is a semicircle, radius 2. Center is going to be at 0, 1. But so this is the semicircle is located above the x-axis, so we're going to have a semicircle plus a rectangle, and the area of the circle, a semicircle, 1/2 times pi r squared, and the radius here is 2, so it's going to be 1/2 times pi times 2 squared, or 4 pi. The area of the rectangle, it's length times width, so it's 4 times 1, which is 4. So that the area, the integral, then is going to be 2 pi plus 4. Okay, so that's using geometric methods, but we're mostly we're going to be working with functions where we're not going to be functions other than straight lines and circles. So we're going to have to be using other methods, which we'll get into a little bit later. But there are these few examples here where you can use geometric methods. Okay, so here we have a sum of integrals, all of the same function, but over different intervals. We want to write this as a single integral. So we have the integral from 0 to 3, plus the integral from 3 to 7, minus the integral from 0 to 1. So we have let's say the integral from 0 to 7 here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. 1. So we have let's say the integral from 0 to 3 is, I'll put that with a plus. I'll put it in blue for plus. And an integral from 3 to 7, I'll put that in with in blue. That's a plus. And we're subtracting the integral from 0 to 1. So that's, I'll put that in red. That's what we're subtracting. So we want to add the blue parts and subtract the red parts. So the net result is going to be the integral from 1 to 7. So this is going to be equal to integral from 1 to 7 f of x dx. Integral from 2 to 9 plus integral from 2 to 3. From 3 to 2 rather. Okay, so if you reverse the direction of, if you go in the opposite direction, you change the sign. So this is going to be the same as the integral from 2 to 9 minus the integral from 2 to 3. Okay, because if you here we're going from the larger number to the smaller number, so that's normally you go from smaller to larger, but if you go from larger to smaller, it takes the opposite sign. So this is going to be minus the integral from 2 to 3. Let's see, we'll have 1 to 9. 1, 2, 3, 4, 5, 7, 8, 9. And we have 2 to 9. 2 and 3. So we have the integral from, I'll put in blue, I'll put integral from 2 to 9. And in red, what we're subtracting off is integral from 2 to 3. And so the net result is going to be integral from 3 3 to 9. Go from 3 to 9, f of x dx. Okay. Okay, some more examples here. Here we're given a limit here, and we want to express it as an integral. So we're just sort of applying this definition in reverse. The f of x, the integral fx dx is equal to the limit of this sum here, right? So we're just I equal 1 to n f of x I star delta x. So we're just using this definition in reverse. We're starting with the limit and going to write it as in integral notation. So it's just a sort of a change of notation here. So this would be so it's over the interval from 1 to 4. So it's going to be an integral from 1 to 4, and this is going to be this could be 2 plus 3x. 2 plus 3x. And delta x we can write with dx. So when we take the limit, delta x becomes dx. And this piece here, this is f of, this is 2 plus 3x. And this piece here is dx. Okay. And this one here, part b, the integral is from minus 2 to 2. And here's our function. It's 4 minus x squared dx. This one here is integral from 2 to 6, and 1 over 1 minus x dx. This one is integral from 0 to pi sine x dx. Okay, so that concludes this presentation.